October of 2022 sees the release of NVIDIA's new GeForce RTX 40 series of graphical processor units, or GPUs, that are designed to reset the state of the art for 3D rendering in games and high-performance computation. Perhaps the biggest and most exciting element is the introduction of DLSS 3, an AI-powered rendering technique which promises to not only generate outstanding image quality at 4K resolution, but improve graphical performance in a given game by up to 4 times when compared to traditional 3D rendering by not just increasing the resolution, but also the game's frame rate. I'm Tommy Thompson, welcome to AI in Games, and in this video, with help from the folks over at NVIDIA, I'm going to do a deep dive on explaining how DLSS 3 actually works, and showcase how this new technology performs when running games on an RTX-4090 graphics card. The big innovation in DLSS 3 is that it doesn't just up-res the frames rendered from the game to higher resolutions, it uses a brand new component in the RTX 40 series GPUs to generate entire frames of the game by itself without consulting the game engine. It's actually increasing the frame rate of the game by effectively letting the AI guess what the frames will look like in between the game engine's output, and to great effect. It's pretty crazy, to be honest with you, but after testing it quite extensively, I'm happy to report that it works incredibly well. Naturally, this is a far from simple and straightforward process, so strap in folks, we've got a lot of ground to cover. For those new to DLSS, or you're new to this channel, I've already made an entire video exploring how the original version of this technique works in detail, and I recommend you check that video out first if you have absolutely no idea what I'm talking about. Right now, I'm going to quickly summarise how the previous versions of DLSS worked, and then get into the nitty-gritty of this third iteration of the technology. Since 2018, the revolutionary element of the NVIDIA GPUs is the adoption of AI technology in order to yield increased graphical performance. The GeForce 20 series, released in 2018, introduced the Turing GPU architecture, named after the British mathematician and forefather of artificial intelligence, Alan Turing. These graphics cards were now comprised of general-purpose compute or CUDA cores, RT cores that enable for real-time ray tracing, and lastly what are known as tensor cores. Tensor cores are derived from existing technology used for training deep learning AI systems, and are built to enable fast and effective matrix mathematics, which is a common requirement for both training and executing deep neural networks. This enabled for the introduction of Deep Learning Supersampling, or DLSS, a super resolution technique that runs natively on the graphics card, in which the GPU first generates a frame from the game engine at a lower resolution than desired, and then using DLSS, powered by the tensor cores, it up-reses that image to be of higher quality, but it does so using far less power and memory than the GPU would have done if it did it in-game. So in essence, you could get a given game to generate an image at 1080p only for DLSS to up-res it to 4K, and it would be less expensive than getting the game itself to render in 4K. This process has continued to evolve since then, with the GeForce 30 series of GPUs running an updated version of the same architecture called Ampere, named after the 19th century French mathematician André-Marie Ampère. The main difference between versions 1 and 2 of DLSS was that the original required bespoke deep neural networks to be trained for each game to work at higher resolutions, and then the drivers had to be updated frequently to provide the pre-trained deep neural nets for each title. However, with version 2, the process changed to rely on a generic super resolution network, pre-trained using NVIDIA's supercomputer technology. The other big change in version 2 was the introduction of motion vectors, whereby the system gathers information from the game engine on how pixels are moving from one frame to the next, in order to make it generate smoother images for faster moving elements. This is an idea that actually comes from the world of video encoding, and will prove critical for this big step into DLSS 3. So let's discuss how DLSS 3 works in summary, and then I'll get into the details. DLSS 3 builds on the existing infrastructure of DLSS 2, but it also adds in something entirely new, a concept known as optical multi-frame generation. This is an idea that addresses a limitation of the earlier versions of DLSS, namely that while upscaling worked nicely, the boosts in frame rate were often quite limited. DLSS 1 and 2 were good at allowing you to increase the resolution of your games without pushing the graphics card to its absolute limit. This meant you could potentially increase the rendering frame rate of your game as well, given the GPU could handle that increased workload. since it's cheaper to get the graphics card to generate frames at lower resolution and upscale them with DLSS than trying to render them outright in the higher resolution without the AI feature enabled. So for example, instead of trying to run the likes of Doom Eternal natively at 4K with ray tracing enabled and struggling to hit 30 frames per second, you could instead render it at 1080p, and with DLSS upscaling to 4K you could possibly push that frame rate closer to something that's more fun to play on without killing the GPU. This is of course quite valuable for a lot of people given you're all buying nice 4K monitors that can run at 120 or 144 Hz, and as such you want to push the frame rate the game renders at to increasingly higher limits. But of course, the need to render more frames is creating a separate pressure on the graphics card to do a lot of work. And in some games it's difficult for existing GPUs to hit that limit, and that's where DLSS 3 comes in. What DLSS 3 is doing is really quite interesting. It still increases the resolution as before, but now it can also increase the frame rate of a game by using deep learning AI to create new frames of the game in between the ones it receives from the game engine. The optical multi-frame generation I mentioned earlier is looking at the frames being upscaled and in a process that combines information from the game engine alongside its own analysis of the upscaled frames. It's effectively guessing what the next frame of the game should look like. And that's kinda bonkers. But as you can see already from the footage in this video, this is working remarkably well, and that's in part due to how it expands on the existing DLSS 2 technology. Now, let's dig a little deeper in order to explain how DLSS 3 works, and critically how it differs from the previous version. DLSS 3 is essentially three different NVIDIA technologies put together. The first is the DLSS Super Resolution, essentially what we've already seen from DLSS 2. The second is the optical frame generation that is injecting new frames, and lastly there is NVIDIA Reflex, a programming API designed to reduce latency that has actually already been around for a couple of years. DLSS 3 is possible thanks to the GPU receiving a revamp, with this new architecture having a significant increase in tensor cores. This architecture, named after Ada Lovelace, the woman cited as being the world's first programmer, comes with a significant increase to the AI processing capabilities. The RTX-40 series of graphics cards carries the new 4th generation tensor cores, with not only an increase of 512 cores compared to only 336 of the 3rd gen versions in the RTX 3090 Ti, but these new cores achieve up to 5 times the throughput of their predecessors. But perhaps more importantly, the RTX 4090 now has 305 of the optical flow accelerator or OFA cores compared to 126 in the RTX 3090 Ti. This is a huge boost to the GPU's processing power, not just because of the increased number, but also, much like the tensor cores, the OFA cores received a revamp for the 400 series. As we'll see in a second, the OFA is critical to enabling the frame generation. So as stated, DLSS 3 essentially builds on the existing implementation, so let's dig a little deeper into how DLSS 2 originally worked. Previously, the process was relatively straightforward. The game engine would render out the current scene of the game to an image at, say, 1080p resolution, and it would then attempt to upscale that to 4K using the super resolution deep neural net loaded into the tensor cores on the GPU. To do this, it requires the rendered image from the game as well as the motion vectors that it receives from the game engine. As mentioned already, motion vectors actually derive from video encoding, and it's designed to make it easier to render videos in a cheap and effective way. A motion vector essentially tells the renderer that for a given piece of pixel data in the image, where it expects that pixel to move on the next frame. To produce motion vectors for the likes of video playback, you run a motion estimation algorithm, which is analysing the direction and magnitude of motion for a given pixel, relative to the previous frames of rendering. This can lead to significant gains in video compression, given it's more cost efficient to render a new frame by shifting the existing pixels around rather than trying to draw them all from scratch. But there is an inherent problem with this, and it comes down to how the motion vectors are generated. In video, we run all this through use of encoders, which takes a little while to do, but afterwards the results are typically fantastic. But for games, it needs to be much more responsive and in real time. So as mentioned, in this instance the game engine helps provide the GPU with the motion vectors for the super resolution. And this is where the problem lies, because while the game engine knows a lot of critical information for the motion vector, like where the player is and in-world geometry, it doesn't always have 100% accurate information needed for every pixel, given a pixel's colour might be influenced by a particular process that the game engine doesn't cache at that level of fidelity internally. So for example, when running real-time dynamic lighting or having smoke or particle effects, these are reliant on computations that will run in the next frame. A shadow is the result of the position of nearby lighting in the game world, and if we're moving around our character, they may be hit by multiple light sources at once, and the game engine might not anticipate that. And that's where DLSS 3 takes this in a new direction. As mentioned already, DLSS 3 starts with the basics from DLSS 2 and then it adds on the optical frame generation. This is how it not only boosts frame rates but ultimately improves the current DLSS output, given NVIDIA have essentially trained an AI to run the motion estimation algorithm in real time on the GPU. To do this, it looks at the last 2 frames it's up-resed into 4K from the game engine and passes them to the optical flow accelerator, which runs on the OFA cores. The optical flow accelerator looks at the frames and generates what is called an optical flow field. This is essentially a motion vector, but it's catching all of the information that in-game motion vectors couldn't calculate because it's looking at the actual rendered frames from the game itself and observing how things changed between them. It's worth mentioning that while the RTX 30 series cards had some of the OFA cores on the chip, the 40 series is now running twice as powerful, and that enables for this to run in real time, as it is here. With this approach, the RTX 40 cards are able to determine in real time how things like shadows, reflections and particles have changed between these 2 frames, and this is how the frame generation is made possible. After running the optical flow accelerator, the GPU runs a deep neural network that is responsible for multi-frame generation in the tensor cores. It's now being passed in 3 pieces of information: the 2 up-resed 4K frames generated by the super resolution network from DLSS 2, the motion vectors from the game engine, and the optical flow field developed by the optical flow accelerator that has calculated the differences between the 2 frames. From this, it now has information on what the last 2 game engine frames look like, how the game engine expects objects to move around, and how the optical flow field imagines more dynamic elements would change as well. It's essentially got information on not just what those 2 frames look like, but how the pixels should shift in between them. And from that, it can then generate a new frame to render as an intermediate between the 2 frames from the game engine. And this is ultimately how DLSS 3 increases frame rates. For every 2 frames rendered in the game engine, both of which that are then subsequently upscaled before the user sees them into 4K, the GPU is generating a 3rd frame, which is what it has calculated to be what the game state would look like in between the game engine frames. What this means is that using DLSS 3, the bulk of the rendering of a given game is actually being pulled away from the game engine, with the AI on the GPU taking on more and more responsibility. If you consider the super resolution, which is upscaling from 1080p to 4K, it is essentially drawing 3/4 of that frame with the AI, with the original 1/4 handled by the rendering from the engine. You then combine that with the frame generation, and if you double a game's frame rate from say 60 to 120 frames per second, then the AI is generating every second frame by itself. This means that ultimately the AI is now generating 7/8 of the pixel data across 2 frames. And this approach could provide continued gains for customers as neurographical rendering continues to improve much faster than what we're seeing in the traditional 3D rendering space. One part I briefly mentioned earlier that is worth coming back to is the NVIDIA Reflex API. As it was explained to me by the folks at NVIDIA, Reflex is a tool that is critical to the function of DLSS 3 in that it's designed to minimize the latency in the game itself. Reflex is an additional workload for developers to integrate into their games, but it isn't exactly new. Reflex was actually released alongside the RTX 30 series back in 2020, and is already integrated in a lot of online competitive shooters such as Fortnite, Apex Legends, and Call of Duty Warzone. The idea is to minimize the latency of the game, meaning that the time taken for the player to press a button to then seeing some sort of response in the game is reduced as much as possible. While some latency is as the result of the peripherals themselves or the TV or monitor you're using, a good chunk of it is in the processing of the game's state and the rendering of said state. While a higher FPS count can reduce latency, you're still at the mercy of intense GPU workloads, since the game is generating a large amount of frames that are then pushed into the render queue for the GPU to process. Reflex is designed to better synchronize the CPU processing of the game input with the GPU rendering output, with the GPU rendering the output by minimizing the render queue and keeping the time from state processing to rendering as little as possible. Given that DLSS 3 is now also taking on more GPU workload, it makes sense that Reflex is critical to the process, given you want to ensure that the GPU output and the CPU workload are being synchronized as best as possible. Particularly given the optical frame generation means that the GPU is rendering extra frames without consulting the game state, so trying to capture player input as quickly as possible seems like a fairly critical element to the process. NVIDIA's series of GPUs are continuing to expand into the realm of high-fidelity graphics, both by pushing further into the realms of 4K resolutions and real-time ray tracing, but also in order to keep up with the pressures of modern games, are continuing to adopt AI as a mechanism to lighten the load. Within the space of a few years, the DLSS technology in the GeForce GPUs has achieved something that was still a fantasy even 5 years ago. Naturally, my focus in this video has been on explaining DLSS 3 to you all, but the footage largely speaks for itself. All the games I tested on that were DLSS 3 enabled saw significant gains in frame rate, and often look just as good if not better than the native 4K versions. It's a significant upgrade, and I'm keen to see how this evolves in the coming years, and at the very least, future episodes on this channel should be looking a lot crisper. The new RTX 40 series launches on October 12th, Ada Lovelace Day of all times. Funny that. And while I only had a chance to try out a handful of the upcoming DLSS 3 integrations, such as Microsoft Flight Simulator, F1 22, A Plague Tale Requiem, and Cyberpunk 2077, there are over 35 titles announced that will be compatible with DLSS 3, ranging from already released games like Hitman 3, The Witcher 3, Dying Light 2, and Spider-Man Remastered, to upcoming releases such as Stalker 2, Lord of the Rings Gollum, and of course, the re-release of Portal with RTX enabled. Which, you know, any excuse to go in and give Portal another go, huh? Thanks for watching this video on DLSS 3, and a special thanks to NVIDIA for reaching out and providing access to the demos recorded for this episode, not to mention, of course, a chance to try out the RTX 4090 to boot, and also answering a lot of the questions that I had on the inner workings of DLSS 3. We're seeing a lot of work in this space nowadays as AI continues to tackle areas outside of traditional game development, and you can be sure I'll have something to say on it in the future. In the meantime, go do the likes, the subscribes, and I'll catch you all in the next video. Take care.